Greetings, this is Group 3. We are going to present our self-learning project on primary cells.
Primary cells are non-rechargeable electrochemical cells that generate electricity through irreversible chemical reactions. This process involves redox reactions, where chemical energy is converted into electrical energy. The two types of primary cells are dry cells and wet cells, and they have various shapes, sizes, and properties. Typical shapes of dry cells include cylindrical and button cells. For wet cells, they are usually cuboid in shape, and they take much larger spaces than dry cells as they have to store a liquid electrolyte. As we discussed earlier, primary cells can be split into dry cells and wet cells. So, are dry cells really dry? Despite their name, dry cells are not actually dry. They contain water as a crucial component of their electrolyte system. In a zinc carbon battery, the electrolyte is a moist paste of ammonium chloride and zinc chloride mixed with water. In alkaline batteries, it is potassium hydroxide solution formed into a gel. Even silver oxide cells contain aqueous electrolyte. The term dry is relative. It simply means that the electrolyte isn't free-flowing liquid like in car batteries. Instead, it's immobilized as a paste or gel. But water is still essential for ion transport and the electrochemical reactions to occur. So, the name dry cell is somewhat misleading. A more accurate term may be paste cell or gel cell. But dry cell stuck because it distinguishes them from the liquid electrolyte batteries that came first.
On the other hand, a wet cell is an electrochemical cell that utilizes a liquid electrolyte that is not in the paste form, but it is aqueous. In fact, what we learned about Chapter 29 about electrochemical cells are mainly wet cells. For example, this Daniel cell shown here uses zinc and copper electrodes and their respective sulfate solutions. Let's go back to the topic on hand, which is dry cells. Here we have a few examples of dry cells. This silver oxide cell is a small, button-shaped battery, typically round in design. As it is very flat, it can fit in devices with a small dimension. In contrast, the alkaline manganese cell features a cylindrical shape and has more capacity than silver oxide cells in terms of milliampere hours.
We can also compare the discharge curves of the zinc carbon cell and the alkaline manganese cell. As shown here, the former typically shows a rapid voltage drop at both the beginning and the end of the discharge cycle. In contrast, the latter shows a small or negligible voltage drop at the beginning and is comparably more stable. However, once it reaches a critical point, the voltage drops rapidly until it is fully discharged. This is because when the cells discharge, the active materials are consumed, internal resistance increases, causing the electrolytes to become less conductive. As a result, these two types of dry cells often operate below their nominal voltage of 1.5 volts for much of their lifespan, which can affect the performance of devices relying on a stable voltage. So, do we have a better option? The silver oxide cell is a fascinating dry cell that delivers exceptionally stable voltage output. Note that the main reactants and products, which are zinc oxide, silver oxide, and silver, are all solids. In electrochemistry, solid substances have a constant activity of 1. Since the Nernst equation shows that the cell voltage depends on activities of reactants and products, which is represented by Q, it means the voltage stays stable at around 1.55 volts throughout the discharge cycle. Here is a comparison between all three types of dry cells discussed. Their properties will determine what types of applications they are suitable for, to be discussed later. As mentioned earlier, silver oxide batteries have the most stable output voltage. They also have the highest shelf life and are the safest in terms of risk of leakage in the electrolyte. This also makes it the most expensive, costing upwards to 12 times more than a zinc carbon battery. On the other hand, zinc carbon batteries have lower shelf life, safety factor, and stability, and hence cost the least per unit.
So, given the differing properties of the three dry cells discussed, what items are the most suitable for powering? Zinc carbon cells are often used in objects that are used infrequently and require low power, making them ideal for inexpensive items like remote controls. Their foldability makes them a great choice for devices that aren't that picky with voltage stability, but recently, they have been replaced by safer and more stable alkaline cells. On the other hand, alkaline manganese cells are designed for applications requiring relatively stable voltage and low, steady power. They are commonly found in devices like computer mice, hearing aid, and portable music players such as Walkmans. In fact, if the voltage drops in a music player, the song will play slower. That's why you want a more stable voltage that can be distributed over a long time. Lastly, silver oxide cells are favored for small, compact products. They're typically used in devices like calculators, security sensors, and cameras, where there's not much space for a battery. As you can see, each type of application demands a different type of battery that will be most economical and suitable for its performance. It is worth noting that some of these primary cells uses are replaced by more popular secondary cells, such as lithium-ion batteries, which is growing rapidly in the market exports due to their ability to be recharged.
Thank you for watching this video. Here is a work distribution, and here is the references.